Hello all, welcome to the video lecture. This is Ramesh Lama. In this video, we'll be discussing about object detection. Object detection is one of the areas of computer vision that's exploding, and it's working far better than the last 5 years ago. And in order to build object detection, we first learn about the object localization. As we have already discussed in brief about the object localization in our last class, let's revise it and go further in detail. Let's start with image classification. We know image classification task is to take a look at the picture and say is there the dog or not. Here we can see the simple example of classifying a dog, and classification with localization means not we have to label and dog, but also put a bounding box or draw a rectangle around the position of the dog image. In terms of classification with localization problem, localization refers to finding out where in the picture we have detected the dog. We will learn about the detection problem where there might be multiple objects like here, and in the picture, and we have to detect them all and localize them all. The classification and classification with localization problem have one object in the image, and we are trying to recognize and localize. In contrast, in detection problem, there can be multiple objects, and in fact maybe multiple objects of different categories within a single image. Like here we have multiple objects like two animals, one dog and cat, and these are of the different categories. So the idea we learn about the image classification will be useful for the classification with localization, and the ideas we learn for the localization will turn out to be useful for the object detection. So we will start with the classification with localization, and we are already familiar with the image classification problem. We can see here in the example, like in image classification we might input the picture into the convolution neural network with the multiple layers, and this can result in a vector of features that is fed to softmax unit that outputs the predictor class. Here we can see we have input image of cat, and we split it into the RGB, and we convolve it with the 5x5 filter, and we have four different filters, and each with the 5x5/3, and this is the convolution output. If the filter is edge detector, sorry, it should be edge detector, not edge detector. And after the multiple convolution and nonlinear operations such as ReLU, we get the feature vector here, and after this we use the softmax, and that will give us the output, and that will predict whether it's cat, dog, or mouse. And this there are three classes, so we need a softmax with three possible outputs. Now if we want to localize the cat in the image, and to do that we can change our neural network to have few more outputs units, and that outputs a bounding box. Here we can see everything is same as in classification, but we add four more outputs here. Like we have except three categories, we add four more levels here, which is for the bounding box, and these are the bx, by, BS and BW. We will discuss about it in detail in our subsequent slides. Here these numbers are used by model to parameterize the bounding box of the detected object. Like here we have seen before, like here is our bounding box, and this bounding box will be parameterized, or it will be defined by these four levels, we can say this, and it will parameterize, or it will define the bounding box. And now let's see how we build the model with the bounding box. So here we have here is our image. So we start by now we can see here four different levels like BX, BY, BW and BH, and we start by specifying the BX and BY, and we specify the then these are specified by, like these are specified by the midpoint of the box. Here BX and BY represents the midpoint. Like we can see here, this BX and BY, in this case this will specify the center of this box, and the training set consists of the object class level and another two there are two more levels like BH and BW. Here BH will specify the height, that would be BH, and width, BW, of this bounding box. So we have got four parameters, four levels, or four levels. This will define the BX and BY will define the center point, and BH will define the it will define the height of this bounding box, and BW will define the width of the box. And now the training set consists of the object class level together with the positional number, and that will specify the boundary box or bounding box. And now we can use some supervised learning to make our model that outputs the class level together with four parameters to tell us about where the bounding box of the object are detected. And in this particular example, the BX might be at like here we can see it might be at around 0.5, and BY might be around 0.5, as we can see here. Like these are almost at the center of the image. So we can say this might be at BX might be at 0.5, or not completely 0.5, but yeah, it's somehow at the center. Like BX is little bit like we can say 0.52, something like that, and BY might be at 0.5, because they are BY is they are at the half away from the from the image. And BH, like we can say that we can also specify that BH might be of around 60, it's around of 60%, and BW like we can say this at 0.6, and BW might be of around 0.95, because it covers almost 95% of the width of the it covers around 0.95% of the breadth or width of the image. So in this way we can specify these four levels BX, BY and BH and BW. And now before we go further, let's see how we define the target level Y. Like once we get these variables, now we can define the target level, or like this might be, this is Y, and here we can see like the output vector or target level Y would look like this. It consists of it's nothing but the vector whose first component, like this vector, the first component is PC, and this shows whether there is an object or not. Like this PC will determine, or it will specify, or it will tell us whether there is object or not. And if the object is cat or dog or mouse, it will be equal to 1. And if there is no object, then it will be 0, or PE will be 0. Then we can say that PC stands for the probability that there is object, and the probability that one of the class will that probability of that one of the classes we are trying to detect is present there. Like if it's 1, then there is the probability that the object is present, the object that we are trying to detect is present. And now this vector looks like this, like y is equal to PC. And now next, if there is an object, then we want then we want to the output bx, by, and bs. Like if there is an object, that is PC is equal to 1, we want the output class C1, C2, and C3, which tells it is class 1, class 2, class 3. In other words, it is dog, cat, or mouse. Like if it is 1, then we can tell like whether there will be C1s, there is another like if PC is 1, then there is another the class level C1, C2, and C3, and it will tell us like whether it's cat, dog, or mouse. And like we assume there that our image consists of only one object, and most of these objects appears in this picture we can see. And if X is the training image, then Y will have the first component PC is equal to 1. Like if X is training image set, then Y will have the first component PC is equal to 1, because there is an object. And then BX, BY, BS, and BW will specify the bounding box. So our training set will need bounding boxes in the labels. Like these are the then finally this is cat, so it's a class 2. And here C1 is equal to 0 because it's not a dog. Like we use C1 for specifying the dog, and C2 is equal to 1 because it's cat, and C3 is equal to 0 because it's not a mouse. Here in our case, like for this particular image, here C1 will specify C1 is the class level for dog, C2 for cat, and C3 for the mouse. And in this case, if PC is equal to 1 and we have BX, BY, BS, and BW, then C1 will be 0, C2 will be 1, and C3 is equal to 0. And among C1, C2, and C3, at most one of them should be equal to 1. And in our case here, C2 is equal to 1. And in case like there may be another case like the problem that PC is equal to 0 and the rest of the and if PC is equal to 0, in this case the rest of the elements of this vector can be any number. Like we don't care whatever it is, we just once PC is equal to 0, then it makes no sense on this case. And finally, once we have these levels, like once we have this output vector, or once we have the training levels, then we can estimate the loss function. And the loss function we use to train the neural network can be defined in this way. Like the ground truth is y, and the neural network outputs like this is the this is the target, and this is the output of this neural network. then the loss function will be the difference of like sum of we take the difference and square it and take the summation of all the differences, and this will be calculated only when it is equal to when y1 is equal to 1, or when object is present, and otherwise we will calculate only the y1, like only this one, or when y1 is equal to 0, or that means when there is no object is present there, then we will not estimate the loss function. We will estimate the loss function only from this y1, because here we can see that y has 8 components, like the first row of the first of the loss function, and that goes from sum of squares of the difference of the elements, that is the loss function that is the loss if y1 is equal to 1. Like we take the loss of all the summation of square of difference, and that's case where y1 is equal to pc. So if there is an object in the image, then the loss can be sum of square of all the different elements. Like we take the summation of all the elements, and if in the other case, if y1 is equal to 0, like that's if pc is equal to 0, in that case the loss function can be just y1 prime minus y1, that is squared, because in that second case all the rest of the components are not important. So we all we care about how accurately is the neural network outputting pc in that case. Like we just see the value of pc, so here we don't care about the rest of the elements. So this is all about the localization. Like in this way we can specify the output level, and we can estimate the loss function, and once we estimate the loss function, then we can backpropagate and train the neural network, and then classify or we can localize the object. And another example is the landmark detection. Like in classification with object localization, we saw how we can specify the bounding box of the object by getting the output of neural networks, which consist of 4 numbers. Like here we have, in case of localization, we have bx, by, and bw. Now if we generalize this example, like in more general case, we design a neural network which outputs just x and y, like just x and y coordinates of the important points in the image, which we call the landmarks. Like we can use it for generating the point or the x and y location of some key points that we call the landmarks. So let's see an example. Here we are building a face recognition application, and for some reason, for example, we want the model to give us the location of nose or lips, like we can see here, or eyes, some location of eyes, or location of nose, or location of the lips. Here every point has x and y coordinates, and we can just have the neural network with the final layer that outputs 2 more numbers, which will be lx and ly, to specify the coordinates of the point, that is, for example, this person's nose. Now if we want our model to tell us 4 corners of the lips or the nose or the eyes, then we can call the points the first, the second, and the third, and the fourth point. Like we can say, like here we can have first point, second point, third point, and fourth point, and so on. And we can modify the neural network to output Like now the output will be L1x, L1y, and L1x and L1y for the first point, and L1x and L2y for the second, for the L2x and L1y for the second point, and so on. And now once we train the model or the neural network, the network can output the estimated position of the 4 points in the person's face. And we can see here, like now in order to if we want the network to output more points, for example different position of the eye or shape of the mouth to see whether the person is smiling or not, we can define some more numbers. For example 64 points. Here we have got the 64 points, and by selecting the number of landmarks and generating a level training set that contains all of these landmarks, we can then have a neural network which tells us where all the key positions or the key landmarks are in the face. Like once we have these points and we train that, we can identify or we can predict these key points or the key landmarks in our face. And here, like for the implementation level, or here we can see for landmark detection or on the implementation level, what we can do is we take an image of the person's face and input it to the convolutional neural network, then have some set of features. Maybe we have it output 0 or 1, like is their face in this or not, and then we have it also the output L, like here at the first point whether there is a face or not, and then if there is a face, if it's equal to 1, like in our previous case that PC, and then we can also have output L1x and L1y and so on, and that goes down to L64x and L64y. And this example has 129 outputs. Like here we can see the 129 outputs, one for the whether face or not, like the first one will tell us whether it's face or not, or like in our previous case this first one will tell us like the PC in our previous case. And if it's 1, then we have 64 landmarks, like there will be 64 landmarks, and into 2, which is equal to 128 plus 1 output units, and this tells us whether there is a face or not, and whether all the landmarks and where all the landmarks are on the face. Like this output will tell us whether it's face or not, and then once if it's face, then it will give us the location of the landmarks, and based on this we can train the network and we can detect the once we train, then we can detect the landmark of the landmark position of the any face. And this is a simple example. And another one is the like similar to the landmark detection. Another one is the another example is pose detection. Like if we are interested in person's pose detection, then we can also define a key position like midpoint of the chest. Like we can just as before, we can here just as in landmark where we had detected or we specified the position of the eye or lips or nose. Here we can also specify the midpoint of the chest or left shoulder or left elbow or wrist and so on. And then we will need a model or neural network that will annotate the key position in the person's pose as well. And once we have the neural network output all those points down annotating, and we could also have the neural network output the pose of the person. And for that, what we need to do is specify these key landmarks, like which may be L1X, L1Y, and which may be midpoint of the chest down to maybe L32X and L32Y. And if we use 32 coordinates to specify the pose of the person, like once we specify this, and we can use this to train our neural network, and then we can detect the pose of the person, or we can detect the person's pose using the convolutional neural network and these locations. And in this way we can use the first we can use the neural network, or we can use the convolutional neural network for the classification. And based on that classification, by modifying a little bit on the output level of the classifier, we can use that classifier for the object localization. And using that object localization, by modifying a little bit on the output of the object of the localization model, we can use that localization for the landmark detection. And by using the knowledge of landmark detection, we can use the model for the pose detection. And in this way we can use this convolutional neural network for the different applications in the computer vision. And in the next video we'll be discussing about the object detection in more detail.